Greetings, students. So, for this lesson, we are going to do some basic checks, right, on an ignition system, and in particular, a waste spark ignition system or a distributor-less ignition system. So, on this motor vehicle here, we have the waste spark or the distributor-less ignition system, as you can see, right, on this 2000 Hyundai Accent motor vehicle. Alright, so here we have two ignition coils, right, and there are 4 spark plug wires. Alright, so we're just going to do some basic checks. So we're going to start off by checking to see if our ignition coil, right, has power going to it. So if it's a case where you have a no start condition and your vehicle unable to start, it could be that the ignition system is malfunctioning. Right, so what we're going to use here, we're just going to use a simple test light, right, to do our power and grounds checks. We are just going to simply connect our test light to a known good ground, right, and preferably battery negative here. Right, so based on service information that we have looked up, right, the power feed to our ignition coil is this orange wire here, and the ground wire, right, is this blue wire here. So this blue wire here is what we refer to as the control wire. Right, so this is a computerized ignition system where the ground wire, right, is pulsed on and off by the ignition control module or the ECU, right. So this is our power feed and this is our ground wire, the power feed. Okay, so we are going to start off by checking the power feed, right, to our ignition coil and also the ground wire. Right, so I just want to point out here that, so let's say you are unaware of the which wire is power and which one is ground, you could simply unplug, right, the connector, right, from the ignition coil and just measure the voltage, right, on both wires. Right, so the power wire, right, would have voltage at all times with the key on, right, while the control wire you would read no voltages. Right, no voltage would be present on that wire until it is being pulsed on and off. Right, so since that we have already know that the orange wire here is our power feed, we're just going to use our test light to see if we are getting power to the ignition coil. Right, we're not getting any power. Right, so what we're going to do now, we're going to check to see if the ignition is in the on position. Alright, so the key is now in the on position. Alright, so they can clearly see here, right, our test light is bright, right, on the power wire to our ignition coil. Right, so another check that can be done, right, is to check to see if the windings within the coil here is open, right, or if everything is intact. If the primary section of the ignition coil is intact, right, so we should have voltage going through, right, coming in on the power wire here and getting out, right, on the control wire here. So again, with our test light and battery negative, if we should place the test light here, right, on the terminal for the control wire, we should have a light. So what that is telling us is that the primary winding, right, of our ignition coil is intact. There's no breakage. Right, with the ignition coil, right, having power or I get into it, right, it doesn't mean that the ignition coil is able to produce a spark. For it to be able to produce a spark, the magnetic field must be able to build up, right, and collapse. Right, and what causes the magnetic field to build up and collapses, right, to induce a voltage within the secondary winding, is by controlling the ground, turning the ground on and off. So with the ground on, current is flowing through the ignition coil primary, right, and building up that magnetic field. When the ground is removed, the magnetic field collapses. Right, so we're going to check to see right, if the computer is able to, or the ignition control module is able to produce, right, a ground, right, or switching ground, turning the ground on and off for this ignition coil here. So again, we're just going to use the test light to do this, right. Again, our test light is going to be placed on battery negative, right, as you can see here, right, and we're just going to place the test light here, right, on the control wire, right. So right now we are seeing a brightly lit test light. So with the engine running, right, or with the engine cranking, with it running or cranking, the test light should be flickering, right. So we should see that light flickering, right, indicating to us that the computer is applying, right, a ground, right, and removing the ground, able to control the ignition coil for us to produce a spark. Okay, so what I'm going to do now, I'm going to start the engine, right, to show you that the ignition control module or the ECM or the ECU is able to control the ground, right, to this ignition coil, right. All right, so now the engine is now up and running, right. So we're just going to place our test light on the control wire, right. So here's our control wire here. Placing the test light on the control wire. So as you can see here, the test light is able to flicker on and off, like that. Flickering on and off. As you can see, it is flickering. That is indicating to us that the ignition control module or the ECM or the ECU is able to control the ground, right? Pulsing the ignition coil on and off. And it is also telling us that this wire, right, from the ignition coil all the way back to the ECU or the ignition control module, it is good, it is not open, right, or it is not, there's no breakage within it. The next check that we are going to perform, right, is with our oscilloscope. So what we are going to do, we are going to measure the current, right. We're going to graph the current that is flowing into the ignition coil, right, current flow of the ignition coil, and also we're going to measure the primary voltage of our ignition coil. So the primary voltage and current waveform of our ignition coil, right, our two-wire ignition coil here, can tell us a lot about the state of our ignition coil or the state of our system, or ignition system by extension. So we can use that to ascertain things like if we have a misfire, secondary misfire, or if the ignition coil itself is shorted out, right? Right, okay, students. So what we're going to do now, right, we're going to go a little bit high tech, right, in testing this ignition system now. So we're going to use our digital storage oscilloscope. It's a PC-based oscilloscope, right, and our laptop, right, to capture the current, right, and primary voltage waveform on this ignition system. So why would we want to look at the primary voltage waveform and current pattern of our ignition coil? That can tell us a lot about the state of our ignition system, right, by just looking at the primary current and the primary voltage waveform on the system here, right. Current and voltage waveform can tell us that if, let's say, we have a shorted out ignition coil, or if we have a misfire, let's say one of the plug wires here are not on properly, there's a leakage in one of these plug wires or whatever, we can pick it up within the waveform, right. So by analyzing the waveform, that can tell us things like that. So what we're going to do now, so this is the arm clamp. The arm clamp is connected to the oscilloscope over there, right. So our probe here, or lead here, is connected back to the oscilloscope. So this is what we're going to use to measure the primary voltage, right, on this ignition. Right, we're going to start the engine up, right, and capture those waveforms, right, using our oscilloscope, and then we're going to analyze the waveforms that we have captured. So the engine is now running, right, and we are capturing our primary current and voltage waveform using our digital storage oscilloscope. let us now analyze the current, right, and voltage waveform, and in particular the primary current and the primary voltage waveform that we have captured using our oscilloscope right, on our 2000 Hyundai Accent motor vehicle. All right, so the blue trace, right, this one here, this is our current waveform, right? The red trace that you're seeing here below, this is our voltage waveform, primary voltage waveform, right, of our ignition coil. So we're going to analyze the waveforms individually. All right, so what I'm going to do now, I'm just going to turn off the channel for the primary voltage, right? And we're just going to focus now on the primary current, right, by itself. So looking at our primary current waveform here, right? This waveform here can tell us a lot about the state of health of our ignition coil, right? So let us start off with this section here. So I'm just going to divide the waveform up into three sections, three particular sections, right? Just going to start off with here, right? That's section 1, and from here to here would be section 2, and this would be section 3 here. All right, so let us start off with this section here, from here to here, right? So what this section is telling us, this is telling us that there's no current yet, that there's no current that is yet flowing into the primary section of the ignition coil. So in essence, the ignition coil is off. There's no current flow, right? So starting at this point here, right here, right, going all the way up to here is when we have current flowing into our primary section of our ignition coil, right? So current flowing into the primary section of the ignition coil, this is telling us that yes, the computer, right, or the ignition control module is able to turn the primary section or switch the primary section of the ignition coil on, so we can have that current flowing into the primary section of the ignition coil and that magnetic field building up inside of the ignition coil, right? The last section here, right here to here, is when we have the current, right? Current flow stops, right, and it drops or falls all the way back to 0, right? This is telling us that the computer is also able to turn the primary section of the ignition coil on and off, right? So if, let's say, we're looking at a waveform where we weren't seeing where the current, right, wasn't falling back, right? The current is not dropping back to 0 after a period of time. That would be an indicator to us that probably the driver inside the ignition control module or the ECU or PCM is faulty, right? Or it is or the control wire leading from the ignition coil to the driver data short to ground there, right? Where we have constant current flowing into the primary section of the ignition coil, right? So let us do some further analysis on, right? So we're going to look at this little section right here. Let me just put a ring around that. We're just going to look at this little section right here where you see that that little ring around, right? So within this section here, you can see like we have some movements, some little humps, right? Up and down within that little section right there, right? That little section there, right, is telling us something about our ignition coil. And in particular, right, it is giving us an indicator about the state of health of the secondary winding, right? So this part of the ignition coil is referred to as what we call the turn-on oscillation, right? Not all coils will show you a turn-on oscillation, but most coils will show you a turn-on oscillation. And the turn-on oscillation, right, is telling us that the secondary windings inside of our ignition coil is in good state of health. It is not shorted, right? So let's say if our turn-on oscillation here was missing from our ignition coil, right here, it would be an indicator to us that the secondary section of our ignition coil, right, is shorted, right, and that coil needs replacing, right? So let's say, for example, again, we're looking at a coil where we are seeing a vertical upward movement in current and not a ramp, right? Not a diagonal ramp like what you're seeing here, right? So let me just draw that on the board, draw that, show you right there. Vertical movement up like that, right? The current, right, moving vertically up like that. That would be indicating to us that the primary, right? The secondary winding inside of our ignition coil is also shorted, right? And our coil needs replacing. Right, so let me just zoom in on this section here for you on the turn on oscillation section of our ignition coil to show you what I'm talking about. So let's zoom in on that section there. Right, so this is the turn on oscillation that I'm talking about. Right, the oscillation you can see some ups and down in the movement of the current. Right, that's our turn on oscillation. And then again, our turn on oscillation indicates to us that the secondary winding, right, is in good health, right, and it is not shorted. Okay, and again, if our current pattern, right, if there was a ramp, right, a vertical ramping up of the current, that would also indicate to us that the secondary winding inside of our ignition coil is also shorted. To determine the dual period of our ignition coil. Dual period simply means that the length of time that the ignition coil is energized for, right? So let us measure that with the cursor there, right? And as you can see, right, so we're going to measure from the point where the current ramps up, right, to where the current starts to fall back down to 0. So as you can see right here, we're seeing 4.9 milliseconds, right, of turn on time. So this is our dual period. So our coil was energized for 4.9 milliseconds, right? So that's our dual time there. I also want to point out to you that not all ignition coil primary current wave pattern will be looking like this, right? You will find some where you will see the current waveform, right? You have a flat top like that, something like that right there, right? The top is flat like that, right? So if you see something like that, it's not cause for alarm, right? That is just simple telling us that the PCM, right, or the ECU is employing what we call a current limiting strategy, right? So the current limiting strategy is basically we are limiting the amount of current. It is limiting the amount of current that is flowing into the primary section of the ignition coil, right? Thus preventing the coil from being overheated, right? So if there's too much current flowing into our ignition coil primary section, the coil will become overheated, and once the coil becomes overheated, right, it will burn up, right, and be of no use to us again, right? So this pattern that we're seeing here, right, on this 2000 Hyundai Accent motor vehicle, we are not utilizing a current. The ECU is not utilizing a current limiting strategy, right? So we can see we have the maximum rise there. So we can also measure the current, the amount of current that was flowing into the primary section of this ignition coil here. So as you can see there, we are about 4.5 amps, right? That is typical for a for a coil of this nature, right? And based on service specification, that's the amount of current, right, that should be flowing into the primary section of this ignition coil. Right? So what we're going to do now, we're going to look at the primary voltage waveform. So I'm just going to turn off the primary current. And also, what I want to show you again, right? So let's say we had a before I go to the primary voltage waveform. So let's say we have a coil, right? That is not that has a shorted primary windings, right? A coil with a shorted primary winding will look something like that. You will see a pattern looking like this, right? It ramps up vertically like that, right? And you will see the pattern moving over like that, right? That would indicate to us that there's a short, right, in our primary windings, right? And if there's a short in the secondary winding, right, this is what we would see here, right? You would see there's a little vertical movement like that, and then will have that little ramp going up like that. And that would indicate to us that they have a short in the secondary section of our ignition coil. And also if the turn on oscillation is missing from the waveform here, right? So let us now look at the primary voltage. All right, so looking at the primary voltage, this is the primary voltage that you're looking at here, right? So on the primary voltage waveform here, right, when there is no current flowing into the primary section rather of our ignition coil, right, we should be seeing, right, should have 12 volts there on our primary current waveform, right? So when there's no current flowing into the primary section rather, right, we're seeing 12 volts right there. So we're going to see a drop in voltage. So here we see our voltage drops all the way down right at this section right here, where our voltage drops down from here, it drops down to about 0 volts there. That is indicating to us that the transistor or inside the ECU or the PCM has grounded the primary section of the ignition coil, and we now have current flowing into the primary section of the ignition coil, right? And from this point here, right here, all the way over to this point here is when we have current flowing into the primary section of the ignition coil. And in other words, that's our dual period, right? So we can also measure our dual period there, so using our cursors. So if we measure from that point there, that point over to that point, right, we're seeing that 4.9 milliseconds of on time, 4.9 milliseconds of dual period, right? So as we can see, where our dual period ends here, right, when the current flow stops, right, the magnetic field collapses, right, inside the primary windings, right? And what we have happening inside the primary windings is what we call self-induction, right? So the current, the magnetic field that was building up inside of the primary section of the ignition coil from this point up until this point is no longer there because current flow stops. So it collapses and induce a voltage into the secondary windings, right, by what is called mutual induction, right? And also induces a voltage back into the primary section by the way of or what is called self-induction. So it is this voltage here that we are measuring here. So as you can see here, where the voltage was at 0. So this is the voltage, right, at this point here is at 0, right? And it ramps all the way up to 122 volts there, right? That is being induced, right? That is being induced back into the primary section of the ignition coil, right, by means of what we call self-induction, right? So how high or how low the voltage is, right, can also determine the health, right, of our ignition system. So let's see a section right here that we need to look at, right? You need to pay keen attention to, right? So we can see here where this voltage spikes up, right, and it falls, right, and it kind of level off right here. So from this point here, right here, right, to this point right here, right? So from here to here is what is referred to as our burn time, right? Burn time simple means that the length of time that the spark remains at the tip of the spark plug for. And we can also measure that. Right? So typically our spark should last for about 1 to 2 milliseconds. Right? So we should measure that there. Right? So we can see we're having a burn time of around 1.8 milliseconds. Right? So shorter than normal foreign line. So let's say if our foreign line was shorter than normal, it would indicate to us that there is probably a problem with the ignition system itself, right? Could be having
a misfiring event where a spark plug is not functioning properly. It could also be that we have something mechanically wrong with the inside of the combustion chamber, probably loss of compression of valve is not sealed. So continuing with our analysis of the firing line of our wave pattern here, right? So let's say, for example, if our firing line right here, it was way elevated, right? Way elevated all the way up here instead of down at this section here, right? That would be an indicator that there is a lean misfiring event happening inside of our engine. For example, let's say we have an injector that is not firing, or we have too much air getting into the cylinder, right? Or injector that is stuck closed, right, or not delivering enough fuel, right? That would cause our firing line to be way elevated all the way up here. So if we should also see our firing line, right? This section of our firing line right here, dropping all the way down here, right? That could also be an indicator that there is high resistance within the secondary section of our ignition system. It could be that we have a faulty plug wires, faulty spark plugs. Also mean that the spark plug gaps are too large, right, requiring too much energy, right, from the ignition coil to jump that large gap, right? So this section right here, what we're looking at here, it is very interesting, right? So this smooth line that we're seeing right here within this part right here should not be seen such long of a smooth trace right here, right? What that is indicating to us that we could have the plugs, right, the plug wires, right, firing outside of the combustion chamber. We have firing event happening outside of the combustion chamber, so we could have a plug wire that is leaking, right? So this line here should have these hatches, right, all the way across here. Right, so this too long of a smooth line here indicating to us that we have firing taking place outside of the combustion chamber. Right. So let us also do some further analysis on this section right here where the voltage drops right from 12 all the way down to 0. So what that is telling us, that the PCM, right, or the ignition control module is able to ground, right, the ignition coil properly, right? And a properly grounded ignition coil, right, facilitates for the maximum amount of current to flow into that ignition coil, right? And thus by enabling the maximum output from that ignition coil. So if an ignition coil is not grounded properly, right? So let's say if we should measure the voltage, right? And if the voltage was, let's say, when it is grounded, the voltage is at 6 volts or 5 volts, that would be an indicator that it is not grounded properly. And when the ignition coil is grounded properly, right, or any electrical load for that matter, when it is grounded properly, that ground voltage should be at 0, right, or near 0, right, near 0 at 0. So as I can see here, we are at about 921 millivolts, right? So that's near 0. So our ignition coil is properly grounded here. So we have, so with it properly grounded, we have sufficient amount of current is able to flow into the primary section of the ignition coil. And with sufficient amount of current flowing into the primary section of the ignition coil, you can have that maximum amount of magnetic field building up, right? So we can also look at the voltage spike, right, and see whether or not if our ignition coil is grounded, is being grounded properly. Because if an ignition coil is not being grounded properly, the output, the induced voltage into the secondary and also into the primary will also be low, right? And by looking at the current waveform, we'll see a limited amount of current also flowing into the the primary section of the ignition coil. Current flow will be low. All right, so as you can see, just by analyzing the waveforms here, we can see we can tell a lot about the state of health of our ignition system. All right, so we're just going to do some. This is basically the end of the spark event, right? So if these humps here, right, are missing, right, so we should have like about 1 to 4, right, of these oscillations here. Right? So if they are missing from our waveform here, that could be an indicator that we have a spark plug that is full, probably oil filled spark plug, or a spark plug that is shorted, where the center electrode and the center electrode and the ground electrode is touching each other. So there is no way for the spark to jump that gap. Or you could have a shorted coil or dead short within the primary section of the ignition coil. So let's say the spike in voltage here was missing from our waveform. That will also indicate to us again that there's high resistance within our system, and in particular would be on the control wire or on the ground wire, right, or ignition coil, right? So now let us look at both the current and the voltage waveform together. All right, so turning on about the current, right, and looking at both of them together, right? So as you can see here, right, when voltage is at 12 volts, right, we have current at 0, right? So when voltage drops to 0, we have a rising current, right? So that rising current is, you can see that the rising current, right, corresponds with the time in which the voltage remains low, right? As you can see right there, this is when our voltage drops, right? Our current rise, right? And as you can see, when our voltage spikes up, right? That is when our current falls, right? So so this would signify to us, right? The rising voltage signifying to us that the magnetic field, right? Current flow inside the ignition coil has stopped. The magnetic field collapses, right? Okay, right? And the period of time that the voltage is held low, that is the amount of time that current is flowing into the primary section of our ignition coil. So there you have it, guys. We could go much more deeper into the analysis, all right, of the waveforms here, right? But that is what we're going to do. We're not going to go going into it any further, right, for this class.